Hello, and welcome to this DevFest session on workload consolidation for Industry 4.0. And thank you to Intel for putting on this great event. So my name is Alex Wilson. I'm Director of Business Development with Wind River. I've been working at Wind River for around about 20 years, so since the very early days. And we've seen a lot of changes in that time frame. So I thought I'd start off with a brief introduction to Wind River. So Wind River has been in the business for more than 30 years. We're technology leaders in embedded real-time operating systems and embedded software. And we've helped our customers build generation after generation of safe, secure, reliable devices. And to give you a bit of context for that role, we were present in the original Mars Pathfinder rover that went up in the early 90s. And then the second generation Pathfinders, Spirit and Opportunity, and the third generation, the Curiosity rover that's on Mars at the moment. And in fact, the Opportunity rover has been up on Mars working for nearly over 10 years, and it's been given a huge amount of science data back to NASA scientists. So we were founded in the early 80s. As I say, we're a commercial leader within real-time operating systems with a large market share, and we have a portfolio of solutions that address the industrial automation market. We've got around about 1,200 employees. We're a global company in over 20 countries around the world. And we invest 30% of our annual spend, something like 30% of annual spend in research and development. And that's led to some of the interesting discussions we're going to have on today's seminar. So, Industry 4.0. Well, in the context of Industry 4.0, you've probably seen this slide before. We've seen the evolution of manufacturing from the early first generation mechanization concepts through mass production to computer automation and now to cyber physical systems. And Industry 4.0 fits into that fourth generation of the Industrial Revolution, promising to make the whole manufacturing and automation process much more streamlined and up to date in terms of its digital content. And alongside the revolution to cyber physical systems, we've seen this huge industry trend of digital transformation, where we look to take digital technology and optimize our business and technical processes in order to achieve more efficiency, greater market share, new markets even, as we move on in the life of our companies. But what does this mean from a systems point of view? Why are we making this distinction between cyber physical systems and computers and automation in the third generation? And what are our business objectives as we move to these cyber physical systems? So really, this is all about digital transformation, as I mentioned on the previous slide. And in fact, as we look at digital transformation and go back a few years, we see that a lot of projects in digital transformation were about pilots and prototypes on how we might move forward in digital transformation in the manufacturing context. But more and more companies that we talk to now are looking to expand their digital transformation initiatives. And especially in the last few years, we've seen a huge investment in Industrial IoT. And I want to distinguish Industrial IoT from the kind of IoT we see in the press with cybersecurity scares, because I think it's a very different environment in the industrial world to what we see in the consumer world. We have much more control over the products we're deploying in our factories and workplaces. And so we can manage a lot more of the aspects of IoT in that context. And that investment in IIoT is especially around how we can expand our analytics capabilities as we extract data from our manufacturing systems and figure out how we can use that data to make more efficient business processes and gains in OPEX and other business objectives. So as well as looking at optimizing systems, there's a growing business trend to decrease costs in manufacturing. And this is partly to improve profit, but mostly it's to maintain profitability and growth in a very demanding market where we're finding that natural resources are becoming more expensive. The manufacturing workforce is becoming harder to maintain. And one system level approach to reducing costs is through a software-defined architecture. And I'll be talking a little bit about what that means in some later slides. While all of us agree that the end state is software-defined, we have to figure out how we migrate towards that goal and how we address some of the investment we put in legacy applications that we already have running in our factories today. Further consideration for cyber physical systems is that as we connect our systems to extract data and push them up to our analytics capabilities, we have to figure out how we maintain security as we connect our network to the internet and the cloud in order to run those analytics capabilities. And so on one hand, we need this connectivity to reach our goals for digital transformation and plant factory optimization. But on the other hand, we then expose our systems to vulnerabilities we may not have designed them for and increasing cybersecurity threats. So it's therefore mandatory we make sure our systems are secure on delivery and maintain that security throughout their life cycle in the factory, however long that may be. And finally, we need to migrate our systems from automated to autonomous. This shift is essential if we plan to optimize at the plant level and adapt to new customer demand, for example, or make the production system more flexible and resilient. At the same time, if we look at the general trends within our computing architectures over the last 50 years, we have seen swings in architecture design from the early days of centralized mainframe through to the distributed PC era with client server systems to the kind of current mobile cloud centralized environment we're running in today. If you think of our IT systems, a lot of those are now running, the applications are now running in centralized cloud systems with just local clients to access that capability and those services. And IoT, to a certain extent, is now becoming, pushing back towards a more distributed compute environment where smart devices have computing capability of their own. But in actual fact, we at Wind River think that that's not going to be the way industrial IoT is going to go. More, it's going to go to a continuum of computing where we have computing on demand where it is needed. So whether that's down at the device level, operating fail-safe devices or other manufacturing devices, at a local cloud or fog layer, giving you on-premise services that are private within the factory and with very low latency, or full cloud services integrated back into our IT systems. And this more fluid computing architecture gives us a better way of handling the compromise between the massive flexibility and scalability of the cloud and demands for low latency decision-making at the edge devices. I mentioned cybersecurity. This graph comes from the CVE website. I've got the details at the bottom of the graph, which just logs known cybersecurity threats throughout the years they've been recording them. And you can see the tall red bar shows 2017, which was a particularly heavy year for cybersecurity threats. And 2018, even though we're only halfway through the year, is looking to be equally as active in terms of those threats. So we know we need to connect our devices, I mentioned, in order to reap the rewards of industrial IoT. And that connecting these devices will expose them to some of these vulnerabilities. And we have to think about how we protect not only our devices from cybersecurity threats, things like denial of service and things like that, but also the data we're extracting, the analysis we do on that data, and the control systems we're trying to run. And it cascades, because if we think about the protection of the data, we have to think about that data is then going to be analyzed by our IoT system, and decisions are going to be made based on that data. So if we can't trust that that data is real and authentic from our systems and hasn't been compromised, then those decisions will also be compromised, and we could end up making bad decisions that are detrimental to our business environment. Added to this is the necessity to manage and protect private data, especially with new regulations such as GDPR in the EU. This merge of OT and IT systems, along with the promise of highly customized workflows based on customer requirements, and hence customer private data, has to be protected such that we don't expose private data to the world, to the internet, or to other sources. And finally, the fourth item I mentioned was the trend of automatic to autonomous. This graph kind of shows how we move from semi-supervised, more control type automatic systems. You could think of things like a temperature control thermostat, through to automated factories where we program certain things to happen, and then through to semi-autonomous and fully autonomous, unsupervised, no control loops with humans out of the loop, with a computer in full control. And in our manufacturing systems, if we think of an automated plant, we would program our systems to carry out a sequence of complex commands. For example, you might program a welding machine to put a spot weld in one location, move 3 centimeters to the right, put another spot weld there, and so on. And these machines would be isolated from a safety perspective, probably around some form of safety cage. And then operators would monitor the machines to make sure there weren't any problems. But often if a machine failed, while the line itself would have to stop while it's replaced or repaired, resulting in loss of production and increased costs. And as each machine was programmed for a specific task, it's also very difficult to update and change the behavior, making it costly to update the line for new requirements or change the line due to customer demand. As we move to more intelligent cyber physical systems, we want to introduce autonomy into the system. The goal of these systems is that with some autonomy comes the ability to adapt to different situations. Machines can talk to each other within the system and provide some form of self-configuration if needed. Control is managed centrally for the whole plant and line, allowing for systems to be optimized at the factory level. This provides greater flexibility and control of manufacturing, resulting in more overall system uptime and a more efficient overall system. Any errors or issues can be bypassed at the plant level and then planned into maintenance downtime. For example, increasing production speed on a particular line to compensate for a failed machine, or having an adjacent machine pick up some of the spot welds for the machine that failed. Now, this may be a nirvana that we will struggle to reach, but it's a worthy goal. It will require more intelligence in the machines, but also a new system architecture. And this is part of digital transformation as we move to optimize our systems based on digital technology at the factory level. Now, if we look at today's industrial IoT architecture, we've done a good job in connecting industrial environments to the cloud. And the assumption has been that the cloud will have all the new capabilities, and it will simply augment the architecture we have down at the edge and on the factory floor. And this was for a number of reasons. We assumed that the long life cycles of the automation equipment would make it difficult to cloud enable them and adjust them for use in this architecture. Also, the devices down in the factory floor tend to be sole-sourced architecture with proprietary programming models and operational modes. And finally, the product life cycles of these systems is many, many years, so it becomes difficult to upgrade them in a meaningful way that isn't overly expensive. But the trouble with this architecture is that it hasn't really worked out because we don't really get the benefits of IIoT under this environment. Our hardware-based fixed configurations and dedicated functions on our edge devices means it's very difficult to update our production lines and give it the flexibility we need based on the analytical data. And also, it's very, very expensive to update and maintain these devices. As I mentioned, even in this environment, with data being passed up to the cloud and analyzed, you still have to bring the production line down to replace these legacy systems. And of course, these systems were not designed with security in mind. Problems like Stuxnet show us that these devices are not safe once we've connected them through the cloud to our IT backend systems. So we need to think of a new way of implementing these systems. And as I mentioned, one way of doing this is through the concept of software-defined architectures and using virtualization to transform our systems. And we've seen this virtualization transformation in a couple of industries already very successfully. The first one I'm going to show you here is avionics. 15 years ago, Wind River helped transform the avionics industry by developing a virtualization approach to avionics. Prior to this approach, systems were very much distributed across the aircraft with single functions and single hardware boxes that performed that particular function. This is known as a federated avionics architecture. Wind River worked with our leading customers to develop our VxWorks 653 product that implements an architecture called integrated modular avionics, which basically is virtualized avionics applications. In other words, software-defined avionics applications. This allows our aircraft to have a very common hardware platform running multiple applications at different safety levels on the same hardware platform. This approach reduces the space, weight, and power requirements of the avionics systems on the aircraft and allows the aircraft manufacturers to implement more functionality in a software-defined way. This gives them more flexibility in terms of how they upgrade their systems in this very harsh safety environment, and also gives them the capability of adding new functions on existing hardware platforms without having to re-architect and redesign a lot of the systems. The value in this supply chain has moved from supplying hardware systems with fixed functionality to providing software applications with much more capability. And this has revolutionized the avionics industry. And we see this on aircraft like the Airbus A380 and Boeing 787 that are running these kinds of architectures with huge capabilities in terms of their avionics environments. We've also seen a similar transition in the telecommunications industry. Again, here we used to have multiple different platforms providing different services, firewalls, radio area networks, routers, all these kinds of things. And we've seen a transition in the telecom market moving towards an approach of network function virtualization. And here again, the idea is that we want to move to a common hardware platform with very high availability and management and detection systems that optimizes the software applications for highest performance and throughput. And that gives the service level agreements that the carriers need to meet the demand of their customers. So our applications, again, that used to be black boxes, the firewall or the radio area network, are now virtualized into software applications that can be deployed on demand across the networking system. So we have much more control of how we manage, how we deploy and orchestrate our systems within that environment. So these are two very different approaches within these two markets that have undergone this radical transformation through virtualization. So let's touch on the underlying approaches of virtualization in each of these and how they differ. In avionics, multiple safety and real-time systems are consolidated onto a single platform. This is what we refer to in this diagram as east-west consolidation. The main characteristics here are real-time performance and partitioning for functional safety. So we need to make sure we isolate our safety functions so that we can maintain that high safety requirement. But at the same time, because we're controlling devices, we have to have performance. We can't have the latency introduced by cloud-based architectures. In telecom, in network function virtualization, we're looking at a more flattening of the topology, running the telecommunications infrastructure on standard server equipment. And the main characteristics here are scalability, performance, and high availability. And this is referred to in this diagram through the north-south arrow. And these two different approaches to virtualization allow us to implement a wide range of system architectures. And Wind River has expertise in both of these types of solutions and market-leading products in both domains. So how does that fit into Industry 4.0 and the concepts behind that? Well, the idea behind Industry 4.0 is starting to become a reality in terms of how we architect and build such systems. With the advent of things like the reference architecture model I'm showing you in the diagram here, we can start to standardize on how we design and build such complex systems. We can see that this architecture describes not only the types of systems along the bottom right axis, the product, the field devices going through to the connected world being our industrial IoT environment. But it also talks about the life cycle, the type and instance of the products on the bottom left, as well as different aspects of the system, such as the layers shown on the right-hand scale. Our business functions, our information, our communications, the actual physical device itself, the asset. So this reference architecture allows us to talk at a systems engineering perspective, describing both the technical and business aspects of our system, giving us a common understanding of how the system's intended to work. As we fill out the standards in this environment, we can start to see how we would build such complex systems for Industry 4.0. One area that's advancing quickly is our description of components within this architecture model. The component is composed of various elements. Most notably is the data itself. If you recall, I mentioned the data is crucial to our industrial IoT argument because it's that data that's analyzed through our analytics services, and that's what we use to make decisions to optimize at the factory level. So this is critical. The other areas within the component model also shows services and functions that manipulate and use that data on various parts of the device. And this is critical if we think about how our continuum of computing is going to work with seamless information flow and modularity as shown in these components, which allows us to move our functions and services to manipulate that data throughout our hierarchy levels. And this is really concepts that fit into the idea of fluid computing and help to transform the industry towards Industry 4.0 concepts. In terms of cybersecurity, this work is ongoing, and one framework that's adapted for industrial automation is the NIST cybersecurity framework. Now, although this is a US organization, this framework has been applied throughout the world in different industries and different concepts. The adaptation of the NIST cybersecurity for industrial automation shows you how you would use this framework to produce a system that protects both our digital control systems and SCADA environment from cybersecurity threats. And really the idea of the framework is that you work through these 5 elements of identify, protect, detect, respond, and recover, and then you map those and make sure you understand how they work in the context of your Industry 4.0 environment and your factory system. So if we think about identifying activities, this is all about how you identify and manage risk to systems, your risk analysis techniques, how your people use those systems, what assets you have in the systems, what data are you enabling that pushes up to our IIoT system, and what capabilities that you need to be operating in order to run your business. We then develop and implement safeguards against that in our protect cycle and add activities to identify particular occurrence of those identified threats from the first stage. We figure out our response, what actions will we take in our system, and we figure out what resilience and recovery activities we need to put in place to make sure we maintain our business environment if we're attacked. So this framework gives you a nice way of thinking about how you can protect your system as you implement your cybersecurity strategy and figure out your security policy within your factory environment. So let's look at the software-defined architecture in more detail. What does that actually mean? So virtualization gives us the capability of producing software-defined systems. In a single CPU, this was achieved with a time and space partitioning environment, switching the time on the CPU and the memory environment for each application. But with the advent of multi-core devices, we can now implement these systems with very little degradation of performance. We don't need to share the CPUs if we need high performance on a particular application. So in this system, our 3 separated standalone proprietary systems, our control function, our communications, and our HMI, running across with a data bus, can be migrated to a single common hardware platform. This gives us much more modularity and flexibility, allowing us to be able to update or replace various applications without having to retest the entire system. Virtualization enables the use of guest operating systems, which means that we can host both legacy and open source environments on the same hardware platform. The common hardware platform may be a compromise in terms of capability, but the benefits of a single hardware platform should far outweigh these compromises. For example, we only need to train staff for one system, with spares kept for that one system, and reduce cabling requirements between systems, saving on space, weight, power, cabling, training requirements. So these are huge benefits. Added to that, we can allow additional capabilities with careful design to be added to the system without having to rewrite or retest our current working environment. These new applications can augment and enhance our system by adding new capabilities and utilizing unused resources on our platform. Again, this should mean minimal retesting, no changes to existing applications or to the hardware platform itself. Now, when we consider safety systems, we often leave them out of this consolidation story. This is due to the cost and complexity of developing functional safety systems. However, if we're going to fully realize the goal of Industry 4.0 and get insight into control of all systems, we need to bring them into the picture. We can make use of modern processor architectures to separate our functional safety applications from the rest of the system and create what is in effect a safety island. Here we would test our system and platform software to support robust partitioning between applications and test and validate just the system software and functional safety applications. Our remaining applications do not need such rigorous testing and can happily run alongside our functional safety applications. Any issues with the standard applications will not cascade to our safety application, as we have isolated that through hardware partitioning and our safety platform. From a systems point of view, this reduces our cost of testing, as only the functional safety application needs to be fully tested in that way. All other code can migrate to standard application partitions and have our standard quality testing procedures. The same can be applied to security systems, where we can focus our security requirements where they are needed, for example, on the module that has external interfaces, and isolate our security functions in that security island. As an example, we can protect and isolate any communications from our systems to the Industrial IoT cloud services as a mitigation for cybersecurity attacks. Say a denial of service comes into our communication link, we would detect that. Remember our security framework providing detection of known vulnerabilities. And then our resolution could be to halt that communications partition and restart it with new networking credentials, with a new partition and new links. The rest of the system may see a slight delay in communications as you switch over, but would be otherwise unaffected. And this provides us some resilience against these kind of cybersecurity attacks. Now, our software-defined architecture can thus accommodate multiple functional safety or security islands, controlling many different types of machines. This allows for a huge reduction in space, weight, and power requirements, an increase in flexibility and control, and easier system upgrading within our factory environment. Multi-core processors really disrupt the industrial IoT area. Now we don't have to have separated functions. We can truly move to this software-defined architecture without compromising our performance or the safety of our systems. Size, weight, and power are important still, but now you have cost savings while designing, operating, and upgrading, or even decommissioning our products. With robust isolation provided by our virtualization environment, we can now go from all safety to just safety of our functional applications and move our workloads across to standard applications within our environment, reducing our cost, but providing robust isolation. This gives us much more portability because we're using self-contained systems within our environment and virtualizing them on our common hardware platform. And that gives us a certain protection, again, from hardware obsolescence, because our application can be migrated to a new hardware system that supports the same platform interfaces. And so our workload consolidation abstracts our applications from our hardware, and our hardware and software cycles are separated, allowing us to maintain our software IP and move it across to new platforms much more easily. This leads us to our new IoT architecture, giving a continuum of compute capability from the cloud through the fog layer to our edge devices. Computing is now available where it's needed in our system dependent on requirements, and applications can be deployed across this system to where they need to execute, taking into account latency, performance, security, and safety requirements. The simplification of the edge devices to a standard multifunction common hardware platform with software-defined application greatly simplifies the design of our edge devices and allows for greater innovation of software and services to achieve our business goals. So, in summary, let's see what we've talked about in the last 30 minutes or so. The business benefits of workload consolidation. We talked about how we combine multiple systems into single common platforms. This reduces overall system cost, reduces the complexity of single devices. So we have reduction in failure rate and reduction in the number of spares we need to keep. And it provides modularity and portability, reducing our integration cost and allowing us to reuse our software IP on new systems. All of these work towards lowering our bill of materials cost, our CapEx. We also reduce the number of purpose-built systems on the manufacturing floor, driving us to software and commercial off-the-shelf type solutions, virtual software appliances rather than physical devices. This does change our supply chain, but allows us to manage our operational expenses as we upgrade and update systems and put in new applications. And this also gives us a much lower complexity in terms of facilitating integration of those new applications onto the factory floor with reduced failure rate and, again, reduced spares in terms of our operational expenses. We talked about the idea of safety islands and security islands, and this allows us to isolate functional safety components and items that are vulnerable to cybersecurity threats within our environment. And at the same time, that allows us to update those applications and especially the security protection throughout the life cycle of the device without having to rebuild the entire device and all of the software contained on that device. So again, that gives us reduced update and upgrade costs throughout the life cycle of the device. And finally, we looked at how we could add new content to existing systems, adding through connectivity to the Industrial IoT fog and cloud, and how we can add maybe analytics for analyzing the data we're collecting locally so that we can make decisions without the latency of the cloud fog type environments. This allows us to rapidly deploy new capability on our systems without rebuilding applications that have been tested, for instance, for safety and security. And that allows us to rapidly innovate within our IIoT Industry 4.0 environment. So that concludes my presentation. Thank you for listening, and hopefully we can now open to questions. So my first question here asks, is workload consolidation solutions restricted to a particular hardware architecture? So no, the answer is not really. The virtualization concepts exist across multiple architectures, whether they're Power architecture, Intel architecture, or ARM architecture. What you need the architecture to be able to do, though, especially if you're protecting safety and security applications, is it needs to have that hardware virtualization assist capability. So you need that performance implemented in the hardware and that protection in the hardware to augment the virtualization capabilities of the platform itself. And then that second question here says, what exactly differentiates industrial IoT from a normal, say, consumer IoT system? Okay, so I think this is an interesting question. Thank you for that one. I think in a consumer environment, the types of IoT devices that are being thrown out, smart cameras, smart light bulbs, are being exposed to directly exposed to the internet, where the consumer has little knowledge or expertise in how he would make use of that device and how he would protect that device. And we hear daily about applications that compromise the security of consumer type systems. For example, you might put in a security webcam that's monitoring your nursery, and you think, oh, that's great, I can now keep an eye on what's going on. Little to know that that webcam may be compromised and then exposed to the internet, so that many, many people can see what's happening on that webcam. So the control over that environment is very much left to an inexperienced consumer with little explanation on how that works and how that would operate. With industrial IoT, on the other hand, we have far more control over our system. We have a closed environment that we've been operating in. And as we migrate it to realize the benefits of IoT, we can manage that aspect of the device. We know what data we want to extract from our smart devices, and we have an idea of how the analytics can be used to optimize those devices. We can manage the security of how that data is transmitted up to our local fog network and decide whether we want to then transmit it onto our environment. So I think industrial IoT, really, we have much, much more control over how we manage and extract data and how we implement cybersecurity within that environment. Also, the end goal is slightly different. If you think of consumer IoT, it's all about how we can make our lives easier within the home. How we can automatically switch our lights on or control our heating and those kind of things. With an industrial IoT, you're really looking at how IoT can solve your business objectives. So you're very much tying down your story to how you can optimize your manufacturing environment with a business goal in mind. So you have, in that way, a bounded requirement in terms of your business outcome and objectives, and more control over the implementation so you can protect against cybersecurity threats. So I hope that answers that question. I have a question here about how fast is the manufacturing industry changing to adopt these solutions? That's a very good question. If you read, certainly in the UK, if you read the press about the manufacturing process, it's not moving fast enough. A lot of companies are investing in IoT now, as I mentioned earlier in my slide, and a lot of companies we talk to are talking about how they might think about digital transformation. But a lot of manufacturing industries have not really fully looked at the business implications and business justification to move to these systems. And so adoption has been a lot slower than a lot of manufacturers would have liked. So the answer is probably not as quickly as those of us producing IIoT solutions would hope, but it's certainly moving in the right direction. And certainly over the last year or so, we've seen a lot more movement as companies move to adopt these solutions. The question is, how do you differentiate the architecture with existing IoT systems? That's a good question. So existing IoT systems, I would say, approach the problem from the perspective of adding digital capability to legacy systems. So for instance, you would add a gateway device, maybe connect that to your field bus networks, extract data from those, and then use the gateway to transmit that up to the cloud. The architecture I'm proposing here gives you much more flexibility in terms of how you optimize your factory environment. the software-defined concept allows you to move your industrial IoT systems from being proprietary hardware edge devices to being software-defined devices. Now, that distinction allows you to orchestrate and manage your entire environment from your control systems perspective. So in other words, you can optimize across the entire plant rather than just optimizing at the device level. And I think that architecture really differentiates it from existing IoT systems. So a question here, do we face companies that are reluctant to go through the digital transformation process, and how do you sell your solution to them? That's a great question, and the answer is yes. We still come across companies that are reluctant to look at digital transformation. We really try and show them some trends in the marketplace that show why they need to think about digital transformation. And actually, if you really open your eyes and think about digital transformation across different marketplaces, you can see that unless you start thinking about digital transformation, then you're going to be left behind in the marketplace and lose your position. And you kind of think about, a lot of companies think, well, I'm in a very niche area, I'm protected against that from the type of work that I do. But you just have to think about companies like Uber and Airbnb and companies like that have really come into a marketplace and disrupted that marketplace in terms of how they offer services and capabilities to systems. So again, with digital transformation in the industrial marketplace, you can just see the big providers coming in and new technologies coming in that will make your technology obsolete. And in that case, you'll be out of business. So if you don't look at it, you're really risking the future of your company. It's an interesting process, but kind of good to open people's eyes to the capabilities here. Another question's come in that asks, are there particular industrial segments using workload consolidation? That's a very good question. Yes, we already see workload consolidation in areas where you're running multiple types of systems within the same device. So, for example, some of the large industrial plant equipment where you have multiple applications operating a particular machine really benefits from workload consolidation. Robots where you have an HMI alongside a real-time control system, alongside some other maintenance functions. Again, workload consolidation works very, very well in those segments. Outside of industrial automation, we see workload consolidation within devices, large medical devices. I already showed two examples within the telecommunications segment and the avionics segment that are also using workload consolidation. I have a further question here. For industrial IoT, is it better to work with third parties for standardization purposes, or is it better to develop everything from the ground up to improve system security? Interesting question. Standardization is essential if industrial IoT is going to realize the goals of digital transformation. You really need to have an architecture that allows for you to have portability across the system and portability and modularity between manufacturers within the system. And this was really disruptive in both the avionics and telecommunications industries. And I think it will need to happen within industrial automation as well. But without that standardization, it becomes very difficult to realize the cost benefits and advantages of moving to this kind of environment. Now, the question is in the context of system security. And often there's an argument for security that it's better to be proprietary and closed and not expose your systems to standardization. In actual fact, I think evidence shows that having open standard systems does allow us to improve overall system security. You still have to go through that rigorous process of implementing a security policy in terms of how you identify, detect, protect, respond, recover from those threats. But having a standardized system means that you can start to reduce the vulnerabilities, for instance, in the protocols you're using, because you have more people using and looking at how those are used, as well as how you can share security problems across the industry in particular areas. And certainly in the avionics industry and the telecommunications industry, they're very good at sharing security threats and vulnerabilities such that everyone can benefit from those exposures and fix systems to improve overall system security. So I think that standardization with third parties is the only way to go, to open our systems and have more open architectures with much more benefits around both improved system security and improved portability and cost savings of code. So I think I've answered all of the questions at the moment within the questions window. If there are any other questions, please post them. Otherwise, I'd like to thank you for listening to this presentation on workload consolidation in the factory for Industry 4.0, and hope that if you have any further questions, please contact Wind River. Go to our website, windriver.com, or send me an email through the interface. Thank you for listening, and I hope you enjoy the rest of DevFest.